We need especially the compression algorithms for challenging the problem of space requirement and transmission boundaries requirement. So we have to, when we are saving any data, especially image, in general multimedia, since we need more space, by using the compression algorithms, we have to compress and reduce the memory space requirements of image data or multimedia data. So for that, compression means reducing the bit size as a representation for the data at hand. So then, rather than using large memory space, it starts using small memory space. For that, there are different techniques available. We classified them into two: static coding and dynamic coding or adaptive coding. Static codings are attempting, given the total data set, like data that comes in textual format or image format. Since we have the chance to capture the whole data, we can use that data for compressing and reducing the memory space requirement. There are different techniques under static. The main ones are Hoffman encoding and entropy encoding. Last time, again, we tried to discuss about entropy encoding. Today, we'll try to discuss about one of the well-known entropy encoding, which is called Shannon-Fanon. Entropy encoding will give us the benchmark up to what level we can go compressing the data. In line with that, Shannon-Fanon encoding is designed. When we are looking at how it works, the first step for static coding, as we said, is calculating the frequency of occurrence of every symbol. And the Shannon-Fanon and Hoffmans are calculating the frequency of occurrence of every symbol in a given data. Then after calculating the frequency of occurrence of every symbol, we are using their frequency for compressing using either Hoffman coding or Shannon-Fanon encoding. When Hoffman encoding works, it starts by taking every symbol as an independent, and every symbols are defined, for every symbols defined tree-star constructed. But when you come to Shannon-Fanon, we are taking all the data together. Then we start splitting them. So the root is containing all the data. But in the case of Hoffman, since every symbols are initialized with the forest of trees, we have to start merging them to create one tree. But in this case, since in the Shannon-Fanon case, since all the data are in one node, that node should be split until all the symbols are taking one leaf node. So then in Hoffman encoding, to begin with, we are sorting the symbols that are forming one tree in increasing order. But in the case of Shannon-Fanon, since all the symbols are initialized with one node, we are following the decreasing order. That means frequently occurring symbols are coming at the beginning, and those which are least frequently occurring are at the end. But in behind, we are splitting the node into two. When we are splitting the node into two, we have to make sure that the two halves are near to each other in terms of frequency. So Shannon-Fanon is working until all the symbols are taking one leaf node. Then finally, like we do for Hoffman coding, the left branch is assigned with 0, the right branch is assigned with 1, or else the left branch is assigned with 1 and the right branch is assigned with 0. The major thing is consistency Always if you are assigning 0, 0 for the left branch, we have to assign 1, 1 for the right branch. So finally, we'll get a code word for every symbols based on starting from the root node by moving down to the leaf node. So every puzzles are giving us the codes that we have to assign for every symbols. So with this algorithm, if we solve one problem as a static coding, the first step for Shannon-Fanon is also calculating the frequency of occurrence of every symbols in a given image data, text data, or audio data. So in our case, to simplify our examples, given a document, the frequency of occurrence of A, B, C, D, E is given. The frequency of occurrence of A in that given document is 15 times. The frequency of occurrence of B is 7 times. The frequency of occurrence of C is 6 times, D 6 times, and E 5 times. Now, since all of them are in one node, and since they have to be sorted in decreasing order, then the root node should be split into two. So we have to form two branches, the 0 branch and the 1 branch. So to form branches, we have to split A, B, C, D, E into two based on their frequencies. So the splitting point should be determined. To determine the splitting point, we have to make sure that the two groups should be as much as possible near to each other, because it's not possible to split them into equal frequencies. So we have to compare what will happen if I split A against B, C, D, E. Then we have to compare it with AB against CDE. Then we have to compare it ABC against DE. So which one is more near? If we split it into A against BCDE, since A is with 15 frequency and BCDE is with 7 plus 6 plus 6 plus 5, which is 24. The difference between 24 and 15 is 9. So A is far from BCDE by 9. What about AB against CDE? AB, when we are splitting our ABCD into AB and CDE, AB is with frequency of 22, 15 plus 7, and the CDE is with 17, 22 minus 17 is 5. So as compared to A against BCDE, AB against CDE are more near to each other. But still, before deciding ABCD, we have to go one step further and compare. What if we take ABC against D? Are they near to each other as compared to A against BCD and ABCD, or far from each other? When we see ABC 22 plus 6, 28, D is 11, the difference is around 11. So when we are comparing their in terms of frequency, it's better to split ABCD into AB against CD, where the difference is only 5 as compared to other points. Then AB comes to the left of ABCD, the root node, and the CDE comes to the right of ABCD, the root node. Then the left node is assigned with 0, and the right node is assigned with 1. Then again, since there are two nodes, two symbols at this point, again we have to split AB into two. A comes, since there are only two symbols, A comes to the left of AB node, then B is coming to the right of B node, AB node. So then at this point, A is an individual symbol, which exists at the leaf node. B is also the same thing. So we completed the left side of ABCD. Then what about the right side? It contains 3 symbols. Split them into 2. We have 2 chances. Either we have to split it at C against D or CD against E. If you compare their frequency, C against D gives us C is 6, D is 11, the difference is 5. But if we split it at CD against E, CD takes frequency of 12 and the E is 5. So the farness increases. As compared to C against D, E, CD against E is far from each other. So we have to take the 2 groups which are near to each other in terms of frequency. So C comes to the left and the D comes to the right of CD. Again, D should be split into 2. D comes to the left of D and E comes to the right of D. So all the left branches are assigned with 0 and all the right branches are assigned with 1. Now, since we have only one symbol at the leaf node, we can start generating code words for every symbol. What is the code word for A? Starting from the root, following the path until we reach to A, we have to concatenate all the binary zeros and ones. But here we have only starting from ABCD root node until we reach to A, we have 0, 0. So the code word of A is 0, 0. The code word of B is 0, 1. The code word of C is 1, 0. The code word of D is 1, 1, 0. As the frequency of occurrence of symbols decrease, the bit depth required for representing them increase. So as compared to A, B, C, D is taking more space. That means more bits. So finally, for A, B, C, D, E, we have 0, 0, 0, 1, 1, 0, 1, 1, 1 as a representation. How much space is required for a text containing 15A, 7B, 6C, 6D, and 5E? In terms of ASCII code, it requires 312 bits, 15 times 8 plus 7 times 8 plus 6 times 8 plus 6 times 8 plus 5 times 8. But after compression, using Shannon-Fanon, since the code word is minimal as compared to ASCII code, the 15S, 7B, 6C, 6D, and the 5E are requiring only 89 bits. So more than 15% compression is possible. But what is the problem of static coding? One, we have to capture the table that we used for compression, such that we have to use the same table for decompression also. If A is represented by 0, 0, when we are decompressing, we have to use the code word 0, 0 for converting into A. So then for compression, we are using again the code word of ABCD, and for the decompression also we are referring to the code word of ABCD. So the code word by itself has to be saved with the compressed file within the same file. That will take space. Another problem of static coding is, unless and otherwise the whole content is available, it doesn't work. So whether it is Hoffman coding or entropy coding, they are working only if the whole document is available. But nowadays, especially, the whole documents are not available. Consider audio files, consider image files, consider data streams. Getting the whole data at one time is not possible. As a result, while the data is available, we have to start compressing those data. So it's not possible to use a static coding like Hoffman coding and Shannon-Fanon coding. For that also, another technique is designed. A technique which is grouped under dynamic coding called Lempel-Zip compression. Lempel-Zip compression is not working like Hoffman coding and Shannon-Fanon encoding in 2 steps. It works in 1 step. As said last time, starting coding requires 2 steps. The first step is for calculating the probability of occurrence of every symbol. The second step is to apply the algorithm for compression. But in this case, in dynamic adaptive coding, Lempel-Zip is one of the adaptive coding. It only follows 1 step. There is no need of calculating the probability of occurrence or the frequency of occurrence of every symbol. So it works for those data which are time dependent. Audio files, video files, data streams. That doesn't mean it's not working for text and image. It works also. If the data is available, we can still compress. If the data, the whole data is not available, still we can apply Lempel-Zip and compress. In fact, nowadays, Hoffman coding by itself is also improved to adaptive Hoffman coding to allow for Hoffman coding to be used for dynamic encoding for those data which are time dependent. How Lempel-Zip is working as an adaptive coding? It takes always whatever data is appearing. By taking that data which is appearing, it's trying to automatically construct a dictionary and include the data into the constructed dictionary. So the constructed dictionary has its own columns. It has an index, it has a symbol, it has an output. So there are 3 columns with, depending on the text or the data that we are compressing, n rows. And the index is automatically generated starting from 1. Whenever symbols are included, the index is increasing, 1, 2, 3, 4, starting from 1. Then we are including symbols that are appearing. But in behind, we have to see how the symbols are appearing. We have to see the patterns. Basically, we are expecting every pixel to appear every time. So the value of that pixel should be taken. If it's also a text, every symbols are appearing. So then every symbol has to be taken. So a pattern like C0, C1 up to Cn is based on the time adjustment appearing in our output device. So maybe the incoming symbol is a new symbol, or the incoming symbol is similar with the previous symbol. So when we are including into the dictionary that automatically constructed, we have to make sure that the same symbol individually or by combining with other symbols appears multiple times. Whenever there are similar symbols individually and by combining with others are appearing within the dictionary, we have to add more symbols to make it unique. So finally, we are creating an output. The output has 2 parts, the prefix part and the new symbol, which is included within the dictionary. The prefixes are the already existing symbols within the dictionary, and the newly added one to make the already existing symbols unique becomes the new symbol. So we have basically 3 options when we are including within the dictionary. Either the symbol pattern that we are including into the dictionary is unique, without adding any other symbol, then our prefix in that case is 0. That means there is only one symbol. With that symbol, there is no other symbols added. So it has no prefix. But if there is a prefix, that means the symbol is already exists within the dictionary. So in place of that symbol, we have to take its index. So we are combining the index of the prefix which exists within the dictionary with the last symbol we added to make the existing symbols unique. Sometimes whatever symbols that we are adding maybe already exist within the dictionary. So we don't have any more symbol to add to make it unique. In such a case, we have a prefix but no symbol which is added to make that given combination of symbols unique. As a result, we are only taking the prefix, that means the index which exists already. We'll see it with the example to make it clear. Assume that we have symbol patterns AB, BC, BCA, BA, BCAA, BCAAB, which are appearing one after the other. So immediately when LZ compression, LZ compression starts working, automatically it creates a dictionary. A dictionary with 3 columns. The index column, string column, and output column. The index column is automatically starts with 1. Then it goes on adding 1, 1, 1, 2, 3, 4, 5, up to n, depending on the size of the data stream that we are trying to compress. So as per the given string, let's say A comes first. So A should be included in the first index. Since there is no index already available within the dictionary, so A is unique by itself. So what is the prefix we are adding when we are generating an output? The prefix is 0. Because A by itself is unique, so there is no need of adding more symbols. So there is no prefix with a given index reference. So then we are taking 0 with A. Again, take the next symbol, which is B, and put that B in the second index. Before we put B in the second index, we have 1 symbols before that, but that symbol is not similar with B, it's A. So then B by itself is unique within the dictionary. So there is no need of adding more symbols. So without adding any symbol, B by itself is unique. So the output that we are generating is with 0 prefix, with no added symbol. B is forming by itself a unique string. Then again go to the given string and take B and include it with an index 3. But we can't take B only by itself because of already B is available at index 2. So to make B unique, we have to add 1 more symbol, that is C. So when we are adding C to B, now we have at index 3, BC. But there is no BC before index 3. If you are referring to index 1 and the 2, index 1 is containing A, index 2 is containing B. So BC is unique. But why we added C? Because B is already available at index 2. So the output that we are generating is the new symbol C is added because there is an existing symbol B at index 2. So 2C is the output, the result of index 3. Then we stop at BC, again take B. When we are taking B at index 4, B is already available at index 2. So since it is not unique, we have to add more symbol. What is the next symbol that we can refer? C. Take C, BC. But still, BC is available at index 3. So again, BC is not unique. So we have to add 1 more symbol. BC, then the next symbol is A. When you are adding A, it becomes BCA. But BCA is not available at index 1, index 2, index 3. So now we have 3 symbols. But just see the last symbol, A. Why we added A? Because already BC is available at index 3. So our output is BC is represented by index 3, and to make it unique on BC we added A. So 3A is the output. Now we stopped at BCA. The next symbol to refer is B. When we take B, again B is already available in our dictionary at index 2. So to make it unique, we have to add more symbol. Take A. When we are adding A, it becomes BA. Is BA available before we put BA at index 5? We have 4 indexes, 1, 2, 3, 4. BA is not available in any of the index from 1 to 4. So BA is unique. Why we add A on B? Because B is already available at index 2. So our output is 2A. So we stopped at BA. A. So the next symbol again to refer is B. Take B and include it in the dictionary at index 6. But B is already available at index 2. So we have to add more symbol. Next to B is C. Again, after adding C, we get BC. And the BC again is available at index 3. So that means we have to add more symbol. A. It becomes BCA. And when we are looking at BCA, BCA is also available at index 4. So still BCA is not unique. We have to add one more symbol. We have again A. After adding A, we get BCAA at this point. አቤት ምንድን ነው ጥያቄ ነው?
ጥያቄ የለም ዶክተር ይቀጥሉ።
ጥያቄ ነው ምንድን ነው?
የጠየቀ ሰው አለ? የለም
የለም ዶክተር።
እጁን የወጣ ሰው አለ?
So when we are reaching at this point, BCAA is unique because there is no BCAA from index 1 up to 5. So why we add the last symbol A? Because BCA is already available at index 4. So we have to take 4 with A, the last symbol. 4 is representing the prefix BCA, which is available at index 4. Again, we stopped at this A. The next symbol to take is B. Take B. B is already available at index 2. Add more symbol. The next symbol to add C. BC. Again, BC is not unique. It's available at index 3. Then in addition, we have to add A. BCA. BCA is also not unique because it's available at index 4. Again, add more symbol. A, BCAA. Again, BCAA is available at index 6. So we have to add more symbol if there is exist. There is another symbol, the last symbol B. After adding B, we have BCAAB. And this string is unique. If it is unique, so we have to take it as it is, but we have to see the last symbol is B. Why we added B on top of BCA? Because BCA is already available at index 6. So 6B. Now this is the output generated by Lempel zip compression. And in place of the given string, the compressed data is saving 0A, 0B, 2C, 3A, 2A, 4A, and 6B. So 0A, 0B, 2C, 3A, 2A, 4A and 6B is taken as a compressed output of the given string ABBCBCABB. One of the advantage of LAMPL zip is the compression can be done automatically just by referring to the output without any need of a code word table like Hoffman encoding or Sherman-Fano encoding. The only thing is we have to split our data into two. That means a data which is containing numeric values and a symbol. So we can split it into 0A, 0B, 2C, 3A, 2A, 4A, and 6B. So then rather than bringing output as the end, we can bring output as the beginning during decompression. So by bringing the output as the beginning, 0A, 0B, 2C, 3A, 2A, 4A, and 6B, then automatically 1, 2, 3, 4, 5, 6, 7 is indexes are created for the given output. The next step is generating the output. When we are generating the output, we have to start from the index 1. Given 0A, what does it mean? We have a symbol called A with no prefix. So then we can take A only. The next symbol is 0B. Again, since the prefix is 0, with B there is no symbol added, so we can take B as it is. The next one is 2C. The prefix 2 is indicating there is a symbol at index 2 which should be concatenated with C. What is that symbol at index 2? That should be concatenated with C. If you are referring to index 2, you will get B. So B should be concatenated with C. So that means we will get BC. So the next output is 3A. With A, we have a prefix 3. And the 3 is indexing the index 3. At index 3, we have a string, BC. So with A, we have to concatenate BC, which gives us BCA. So that means the compression can be done in consultation with the dictionary whenever symbols or streams of symbols or pixels are available. We can automatically construct a dictionary and include it with the dictionary. And after compression, for the decompression also, just take only the compressed data and then split it into prefix and the symbol. Then that prefix and the symbol has to be included in the output column. Since automatically the index is generated, then by referring to the index, we can convert the output into string. So there is no requirements of saving a code word table like the static coding, Hoffman coding, and entropy coding. So with this advantage, it can compress for us whatever we need. Why we are compressing? When we are digitizing the image, we have to make sure that we are saving as much as possible the memory space requirements of the image data because the alarming growth of image data is more than the data, the memory space. So the memory space is still in terabyte, but the alarming growth of data is in petabyte and zettabyte. So to save whatever data that we are getting in our limited memory space, compression is critical. So when we are thinking about digitization, we have to think about compression. Once we have the data required, we can use it for image processing, image analysis, and image recognition. As you said last time, there are different steps during image processing and analysis. The major thing is whenever we think about acquiring image, there is a problem that we want to solve. Think of a problem. A problem is nothing but a gap observed between what's expected and what's already available. To solve the gap or to fill the gap, we need some image processing techniques. And that image processing technique is applied based on the digitized data, because analog data are not easily recognizable by the computing system. The analog signal should be converted into the digital signal, or the analog image should be converted into digital image.